Hi everyone, thanks for joining the Analysis Junior Seminar Series. And thanks Caterina Millevoi for accepting our invitation. She's a postdoc now at the University of Padova. And she's gonna speak about from Porous media to pandemics, harnessing physics-informed neural networks. So thank you again, and when you're ready,
So thank you, everyone, and thank you to Anna and all the PhD and researchers that invited me today. It's a pleasure for me to be here. And just to thank you for the introduction, but just to quickly introduce myself. So yes, now I am a postdoc at the University of Padova. I started my university career in Padova too. I did my bachelor and master in math in Padova, and then I moved to the Department of Civil Environmental and Architectural Engineering, looking for applications. I did there my PhD, and now I am a postdoc. So today I will talk about the main topic of my PhD thesis, that was the application of physics-informed neural network, mainly to Porous media, but also we did a project to apply it to modeling epidemic spreads. And to be honest, I thought a little bit about what to present today, and I decided to just go through our research on physics-informed neural networks, and to also show our open problems, looking for collaborations or ideas, or to share some comments. So I think we can organize a bit. I don't know if I can. Maybe if you want to interrupt me every time you want, please feel free, and I will be very happy to answer your questions and comment a little bit more. Okay, just to start. Okay. This is the outline of my talk today. So I think it would be not necessary to introduce you deep learning, neural networks, and physics-informed neural networks. So it's really a short introduction, just for a matter of notation and to contextualize, let's say, the talk. And then I will move to the application that we made of beam in reservoir simulation, and then in epidemiology, to conclude with some comments and possible future developments. So what is deep learning? As almost everyone knows, deep learning is a subfield of artificial intelligence that contains all those models that are able to learn on their own by some available data, performing progressive extraction from this data. And the core of the deep learning is the artificial neuron that aims at simulating the behavior of the biological neuron that receives signals, elaborates it, and sends it to the following neuron. So the same does the artificial neuron. Receive an input X, elaborates it by means of a linear combination of weight W and biases B, and applies a function that is, yes, here is a labeled here, that is an activation function, in order to give nonlinearity to this operation. And neural networks are just the progressive composition of this operation of these artificial neurons, as many times as the number of layers or the number of neurons per layer, that is a moderate choice. So once you have built your neural network, you have a function that depends on an input X and gives you a corresponding output Y. Here we will label all the neural network output approximation as a hat. And so you have some data, and you want your neural network to approximate as well as possible your available data. So you choose a loss function, that is a function which measures the mismatch between your data and your neural network approximation, and you want to minimize it. This minimization is called training. During the training, the parameters of the neural network, which are the weights and the biases B, are progressively updated by means of a gradient addition method. And the goal of this process is to find the optimal values of those parameters, which corresponds to the to those values that minimize the loss function. And what are pins, which is the acronym of physics-informed neural network, are a particular type of neural network that, in addition to data, allows you to consider some information coming from the physics that governs the problem. So if you know that your problem is governed by a differential equation, you can enrich your data by imposing that your neural network satisfies this differential equation. How it is done? Neural network so contains an extra term in the loss function. So they usually have the common term here highlighted in green, which imposes data fitting, but also another term which imposes the minimization of the residual of your of the governing piece. And so the first term, the terms in which you want to minimize the misfit between your data is usually evaluated on a set of data that are the training data. And while the latter one, the one which imposes the minimization of the residual, is usually evaluated on a set that could be different. And all those points that belong to this set are called collocation points. So while the first set is strictly related to the data that you have, the availability of the data, the latter one is completely independent, so you can evaluate and compute your residual wherever you want in your physical domain. They are mainly applied over two classes of problems. So given a differential equation like this, that would depend on some parameters lambda, you can use a pin to approximate its solution. Or you can use a pin also in the second class that is called data-driven discovery, that takes place when also the parameters involving your differential equation are unknowns, and you want to estimate them by means of your available data, while simultaneously solving your PD. So why we have decided to think about PIN in reservoir simulation? Because we had two main objectives. The first one was the creation of surrogate models that could be alternative or supplementary to traditional finite elements one, for example. And the second objective was the one of parameter estimation, because in this field, the geomechanical and hydraulic parameters could be extremely heterogeneous, and they are usually very hard to be directly measured. So every time you perform an in situ measurement, these measurements are strongly affected by larger errors. And so usually you use different type of measurement that are not direct in order to extrapolate some information about the parameters that defines your field. And PIN have some advantages. They allow you to integrate data while simultaneously solving your PDEs. They are mesh-free, and it gives you differentiable solution that could be easily differentiated by means of automatic differentiation. And so the first thing that we noticed was every time you want to start with a PIN-based model, you have to make many different choices that defines the structure of neural network that is called architecture. So for example, those choices correspond to different values of the hyperparameters defining this architecture. For example, the number of layers, the neurons per layer, the type of activation function, but so many kind of hyperparameters you can set. And so our first goal was to try to understand a little bit if exists the best, a suitable architecture for kind of problems in quantum mechanics. And so we started to build our model, and then we perform an analysis on the impact of these hyperparameters. So we are in the first class, that is data-driven solution. So we're supposed to know the structure of the PDEs along with the values of the parameters and try to solve these PDEs. So we focus on the Biot's model, which is a common model in mechanics, which is simple but still maintains many of the characteristics of reservoir modeling. It is a coupled model, so we have two unknowns, which are displacements and pressure, that are strongly coupled one among each other. And we focus on two benchmarks, one-dimensional Terzaghi problem that consists of a sandy column, on the top of which is applied a constant load, and the two-dimensional problem, which is the Mandel's problem, which consists of a two-dimensional sandy slab that is squeezed from the bottom by a constant force. We choose these two benchmarks because they both have analytical solutions. So we were able to compare our results at no cost and compute as many synthetic data as we want to, again at no cost. So in this setting, the P in the loss function is the result of the contribution of many different terms. We have some terms that imposes data fitting if available. We have some terms that imposes the minimization of these two governing equations. And we have other terms that imposes the boundary and initial conditions. So in this setting, as I said, it is a coupled setting. And this summation could be weird, especially for people that are trained with physics, because each of these terms has a very different physical meaning, and so it would be weird to sum all of them. And that's why here I highlighted these constants that are called weights, loss weights. That have two purposes. One is to make these different physical terms summable, and also to avoid one term overlapping the other during the minimization of the pin, because as you can see, this is a multi-objective problem and it's quite difficult to be minimized. And the first thing that we noticed applying pins in this setting was that the distribution of the training and collocation points, training data points and collocation points among the domain could entail to very different results. Here, for example, on the bottom left plot, you can see a comparison of the errors for initial times between uniform time distribution of the training data points with respect to a logarithmic time distribution. And this, so we just noticed that choosing a logarithmic time distribution would avoid many oscillations for initial times, which is a common problem, quite similar to the ones that arises in traditional with traditional methods. So as you can see from this plot here, this is the distribution of the training points all over the domain. So we have on the y-axis Z, which is the height of the column, y on the x-axis t, which is the time of our simulation. And as you can see, we have a logarithmic time distribution of the data points among the domain. And the same applies for a two-dimensional case. This was the first thing that we noticed when started to apply pin to paramechanics. Then I said we wanted to find if exists a suitable architecture for those kind of problems. So we left the hyperparameter vary in these sets, and so we perform a full factorial combination, and we analyzed all the different 134 combination different architecture that we find out. And these are the errors distribution of corresponding to all these different architectures. So the x-axis goes from 1 to 144, which are the total number of architectures that we considered. The green line corresponds to the mean error for the displacements and for the pressure. And then we have the green bands, which correspond to the standard deviation error bands. And what can be noticed by this plot is actually that the mean average, the average error is quite low because we have around 2 to 5% error. And also the standard deviation bands are quite thin, which suggested us that the method seems to be robust. So, okay, the architecture, we have some outliers, so the architecture could impact, but generally speaking, the method seems to be quite robust to solve those kind of problems. And instead, these are the mean error plots for both the displacement and pressure for the 1D and 2D problem. So the rule here is the steeper the line, the higher the significance of the hyperparameter. And as you can see from the plots, there are some hyperparameters that are more relevant than the others. For example, the activation function for the displacement for now to be an extremely significant hyperparameter. Given this result, we perform a response optimization, and we find out those the architecture that corresponded to the lowest errors. And as you can see from the table that reports the results, these architectures are not that deep, and so this is quite good news because less deep the neural network, lower the number of parameters to be tuned during the training, which is the most tricky part of things. So then, given the results of the sensitivity analysis, we decided to apply them to simply solve the problems. Let's focus on the Terzaghi problem. So we perform a forward solution. So we're supposed to have no data inside the domain here, which corresponds to the left part of the slide. So as you can see, we have only collocation points. So those points which you measure and compute your residual. We don't have any data inside the domain. We suppose only to know the initial and boundary conditions. And once we train our pins in this setting, the training turns out to be extremely long and unstable. And so making the approach uncompetitive with respect to traditional methods. So we propose a sensor-driven approach. So we said, okay, mainly, usually, when we want to simulate a reservoir, we have many data coming from sensors that are spread around the domain. And so we're supposed to have a sensor in the middle of, for example, of the column that was able to measure the quantities of interest for during the time domain. So the difference between the left and the right plot is that we have some data coming from a fake synthetic sensor located at z equal to 7. Okay, and he's able to give us data along the entire time domain. And with this, considering these few data inside the domain, allowed us to consistently reduce the training times and also increase the accuracy of our simulations. Here, the plots on the top corresponds to the loss function behavior during training for the two benchmarks considered. And the blue one is the vanilla traditional forward pin, while the colored ones are the one with the sensor-driven framework that we propose. And also you can see from the errors in the table in the bottom, we have a comparison between the forward case with the case in which we're supposed to have sensors coming from both pressure and displacements, in which we're supposed to have some noise inside these sensors, or which we're supposed to have only pressure sensors. And in all these cases, for sure, the noise will affect our accuracy, but the training and also the final accuracy with respect to the traditional pin were better. And so, actually, just to be noticed, this works applies to a case also in which we're supposed to have a sensor that's measuring. For example, suppose we are in time t star, and we have a sensor that is giving us data from the initial time t0. If we want to forecast the behavior of our simulation, we could also use the sensor that we have until now, and also using this sensor for a part of the domain, the same results applies for our reduction in the training time and for the fact that we were able to increase also the accuracy of our results. This is instead a qualitative comparison between the analytical solution, here in gray, the pin forward solution with no data inside the domain, and the pin with the sensor-driven approach that we propose. And also from this plot, you can see that there is a strong misfit between the red approximation without data, while instead just giving few information inside at fixed location inside the domain allowed us to capture really better the behavior of our solution. Here are some just comments about this sensor-driven framework and the application that we think is more interesting. So, for example, when we are just modeling our reservoir, we have a lot of uncertainties given from, for example, the values, the guess that we have on the parameter values, but also from the fact that actually we know the main physical behavior that is happening in our field, but actually there are a lot of other different physical processes that are affecting our results. And in this framework, actually, if you want to approximate and solve your problem with a traditional method, actually you just simply solve the differential equation that you suppose are governing the main part of the problem that could be affected by some errors. And then your solution is the exact solution or an approximation at a given resolution of your, let's say, inaccurate guess of the physics that is governing the problem. But the fact that pins try to approximate something to solve a differential equation, but they are not strictly forced to satisfy the differential equation, because they can and they do. They balance the residuals with some measurements and data fitting, as we have said, because the loss function is given by the summation of many different terms. And these help make pin suitable in the context in which, for example, you have an idea of your parameters, or the values of the parameters for the field. For example, you know the porosity, you have some measurements and from that you have extrapolates an idea of your porosity and your Lamech constants, which describes the types of material and the geomechanical properties of your reservoir. But actually, this information are inaccurate, given the fact that the in situ measurements are affected by errors or something else. And so here, we just test pin in this setting. So actually, we train our pin with the residual that was inaccurate. So the governing equations, the parameters involved in governing equation were inaccurate, so were affected by errors. For example, here we supposed to have lambda equal to null equal to 40 megapascal and k equal to 10 to the minus 5 meters per second. And actually, we're supposed to have some measurements, and the measurements correspond instead to the real values of your of the parameters that describes your reservoir. here denoted by the star. So the true values of the parameters are actually 50 and 10 to the -4 respectively. And so we train pinning this with these two contributions, an inaccurate residual and some data coming from instead two values, but located only in 3, 2, 1 sensors spread all over the domain. And in this setting, actually, pins turn out to be able to capture the true physics, the actual physics, even if trained with inaccurate physics. So the plots represent this. The gray lines are the actual solution of the differential equations given the true values. The blue line instead are the true solution, the solution of the differential equation with the inaccurate parameters, so the ones of the residual that we use to train it. And you can see how the pin, even if it is trained and it is yes, this is trained to minimize the residual of the blue lines. He's able to capture instead the physics and the behavior of the gray lines, and that are the lines corresponding to which we just added few information at few locations inside the domain. And this is, we think that this is one of the most promising application of pins, because actually if you use a traditional forward solver, you want to solve your inaccurate solution, and for sure you will find the blue lines. Instead, with pins, you are able to balance the information with your available data, and somehow correct your wrong guess on the physics that is covering your domain. Okay, now let's move to the data-driven discovery, which is the second class. So same setting, but actually now we also want to estimate the values of the parameters involved in the differential equation. So just to see how the number of training points, of data points, affects the accuracy of our results, we compared two cases. An ideal one in which we're supposed to have data spread all over the domain, and instead a more realistic case in which we again supposed to have a sensor inside our column that is able to measure the quantities of interest. So in the first setting, this plot shows the x-axis corresponds to the number of data points, and so you can see how there is a monotonic trend of our estimation. So the larger the data set size, the higher the accuracy of our approximation. But in a realistic case, this does not apply to, because you can see that at some point, given some data, adding new data points corresponding to a fixed location does not improve your results, and does not improve your estimation of the parameters. And this is actually this gives us an information that is, okay, I have few parameters, I have few data points, I want to train my model with these points, but I'm not able to reach the real values. Actually, just increasing the number of data points, so spending money to adding new sensors and performing and accumulating new data points is not the right solution. Okay. And let's move instead to a more complex case. Now we are in two-dimensional cases, so same equations, but two-dimensional, and we compare the two homogeneous problems. First one is the consolidation in a homogeneous problem. That is, we have a two-dimensional homogeneous problem made of domains or made of sand, and we have a load that is causing subsidence. And the other problem, the other test case is a two-dimensional. It's the same setting, which instead we're supposed to have a pumping well, that is a pumping water from inside the domain. These two settings has no analytical solutions, so we use a traditional method in order to use this its solution as a reference. And these are the results that we reach in parameter estimation in the two-dimensional homogeneous setting. So the blue lines are the pins that are moving and changing during the training, while the gray lines are the reference solution. And instead on the right, we have the behavior of the estimation of our parameter during the training of the pin. And as you can see in this setting, we were able to reach convergence. A thing that is curious is the fact that the two parameters that we are trying to estimate are actually equal, but this is not, this information is not given to PIN. No, PIN doesn't know that actually the lambda and mu have the same values and the same behavior in the simulation. But during the training, even if the convergence is not reached from the beginning, PIN is able to understand that there is a symmetry between the two parameters. And the same applies in the case in which we have a pumping well. And same applies to the fact that the PIN is able to capture the symmetry. But actually we had some problems. Now we are starting having some problems in simulating the solution. I don't know if you are familiar with reservoir simulation. Actually, these kind of results are quite satisfactory because there is stronger certainty again, but there is still work to do in order to improve the results. But for sure, the fact of estimating the parameter was satisfactory.
Sorry.
Yes.
Next, how do you estimate these parameters here to be differentiation phase? How do you?
They are treated like weights.
Okay.
So they are tuned during, yes, exactly. They are tuning during the training as the parameters that are defining the neural networks.
And I was curious because I was also doing something similar, but so do you try to do something? I mean, the values of the gradients that you apply to the weights and to the parameters, maybe they are similar, but the scale at which the weights are is really different from the scale at which the parameters are. I mean, the value, for example, maybe the weights of the neural networks are on the scale of 10 to the minus 5, while the parameters are megapascal, 10 to the power of 5, for example. Do you rescale some with the gradients or the parameters, or do you?
Yes, it is a good question because it's a tricky stuff in with pins too. Because as I said, this optimization is quite difficult, and there are different ways to solve the fact that these are parameters that have a physical meaning. So you can scale the entire system of equations, right? Instead, we did a different thing. So we scaled the neural networks. So we have a neural network that is representing the scale pressure that has a output range from 0, I don't know, from 0, that is scaled from 0 to 1, let's say. And then we extract another neural network that instead is representing exactly the pressure by denormalizing the neural network. So the way in this way, let's say the fact that the weight of the neural network could increase while because the ranges of the output could be extremely large or different, is less the problem is less affected by this because we just control the range. And so when you usually in deep learning, you control the range, the output range of neural network, you are somehow controlling also the range of the parameters. And so actually this allowed us to solve this problem of different scaling, because both the parameter that need to be tuned and also the quantities of interest, so pressure and displacement, are scaled. But then we minimize the real unscaled residuals.
So you both rescale the output of the neural network and the parameters that you want to estimate.
Yes, and then we use the normalized output to compute the residual.
Yeah, varies to not needed about things, but since you know the structure for your equations, like can't you just perform you assemble the different operators from your data, and then you do like a linear square regression with reach normally reach regression on the last or whatever in order to infer the parameters.
Oh, yes, for sure, it's a different procedure, but the procedure with PIN works like that. I mean, you simply use your neural network to approximate the solution. You can differentiate it. You build your residual, and the residual contains the unknown parameters. Okay, so. Now I move to a more complex case, and this is still an open problem for us because we move to an heterogeneous setting. So same as before, but actually now the domain is not completely made of sand, but we have two different layers, and we're supposed to know the spatial distribution of different materials, but not the nature of the materials, so the parameters that define the two materials. We consider a case in which we have consolidation in this setting, and a case in which we have instead also a pathing well. And in this case, actually, again, the blue lines are the pins that are moving and are updated during the training, while the gray lines are the reference values. And the table shows the results of the parameter estimation. While for the geomechanical parameters, we were able to reach some approximation that were satisfactory for us. For the hydraulic permeability K, that is governing, let's say, defining the hydraulic part of the dynamic, and the geomechanical parameters for the sand, we were not able to reach the true values. And so we just decided to look deeper into these values. Okay. So if we look to the hydraulic permeabilities, actually, what is predicting our pin is the harmonic mean, is an approximation of the harmonic mean of the two values. And this is physically consistent because we are in a case in which we have the flux that is moving orthogonal with respect to the spatial distribution of the different layers. And in this setting, the behavior of the problem is equivalent to a case in which we have an homogeneous material, but with the permeability equal to the harmonic mean of the two permeabilities. So actually, PIN is again catching something that has a physical meaning, for example, the symmetry of before. Now it's catching the fact that we have a flux, so the meaning of the estimation that pins give for the hydraulic permeability could be could have a physical reason, okay, but actually is predicting the wrong physics, because now we are instead in a heterogeneous domain. Instead, if we look deeper into the fact that the values of the lambda and mu parameters are equal to 0, we should just look deeper into the equations. So in the lower part, that is the sandy part, the orange one, pressure, as you can see, this is the plot of pressure. Pressure, each line is the value of the pressure in time. In the lower part, pressure is constant in space. So actually, the right-hand side of our equation is equal to 0. So the solution that is predicting PIN is a possible solution because lambda equal to 0 satisfies the governing equation. But if we look deeper into the fact that displacements are linear in space, also those other two terms are equal to 0. Okay, so actually this turned out to be an ill-posed problem with pins, and we are still thinking about how to solve this. So we are thinking about imposing some boundary condition in the layer between the two different materials. We are also thinking about imposing these discontinuities in the derivatives, but we are still not solved this problem. And so one of the topics that we wanted to investigate more, I said this, I wanted to solve also our open problems, is the fact of exploiting PIN that are defined in the total domain, but when the domain is heterogeneous. Then instead, in the other case, if you have a pumping well, actually this does not apply because pressure and displacement are no more constant or linear in space. And these are the results that we reached till now, and we are still to improve them. Again, if we look to the parameter estimation, they are quite satisfactory too for us because they have an uncertainty that is feasible in the context of the modelization that we are performing, but we have some oscillations and many different problems in approximating the solution. So again, we are still working on that. Okay, just now I will move to the other field of application, that is epidemiology. So what we did with pins in epidemiology, we started from a simple problem that is a compartmental model, SIR model, which describes the interaction between three classes of population during a pandemic. So S is the susceptible class, I the infectious one, R the recovered. And these interactions during the pandemic, the interaction of this population is governed by some parameters. So usually at the beginning, or the total population belongs to the susceptible class, and we have a few individuals belonging to the infectious class. And when the infected population interacts with the susceptible one, the susceptible could move to the infectious class with a rate that is governed by a parameter that is the transmission rate that is strictly related to the reproduction number that during COVID was extremely famous. And after an individual becomes infected, it remains infected for a while, and then after the infectious period moves to the recovered or retired class. So these are the ODEs, the system of ODEs that describes this interaction. Actually, this system is easy to be solved. Okay? The hard thing here is to estimate the values of these parameters that governs the dynamics during the epidemics, because they are extremely time dependent. And so this is why we have thought about pins. So in this setting, we have three unknowns that are susceptible, infectious, and recovered, along with the transmission rate parameter or the reproduction number that is linked to it. So we started from a simple problem. We usually in a realistic application, we have data only for the infectious population because it's not possible to measure the number of susceptible individuals or recovered one. So we just we fixed the parameters to some values that were realistic of COVID in Italy. And we generate a synthetic data set and we perturb it with an error. And then so we built our PIN that is trained on a loss that contains terms that imposes the minimization of the misfit between neural network prediction and data only for the infectious class, which is the only data that could be measured during an epidemic. And then other terms that instead imposes the minimization of the residuals of the ODs. So just few comments on this. Actually, we suppose that the number of deaths were negligible with respect to the total population, and this allowed us to reduce the number of unknowns from 3 to 2, and thus correspondingly reduce the number of parameters to be tuned. And moreover, the range, again, the same problem with neural networks and PIN, the range of these neural networks is extremely large and wide because they could span from 0 to, for example, in Italy, 55 millions. And so we scaled also the neural network, and in this case, we also correspondingly scaled the system of ODs. And moreover, since these neural networks represents the number of individuals in a class, allows only for positive output. And we decided to impose this condition in a strong way by just setting the last activation, so the activation of the last layer of the neural network, to the square function in order to allow only for positive outputs. And this is the first application that we made. So we're supposed to have a constant transmission rate. We're supposed to have only the data for individuals here with the magenta cross for the infectious individuals, sorry. And from now on, the dashed black line corresponds to the PIN prediction, while the colored lines correspond to the true values. And everything seems okay, the prediction is good, the value is, the error is low, but actually if we look to the training time for this really toy problem, was not satisfactory for us. And so we decided to, so we proposed a method to reduce the training time. So actually what we did was to split the training into 2 parts. First, we trained the neural networks corresponding to which we have some available data, here the infectious neural network. So this is the first part that is only data regression, so minimization based only on the available data. And then we train the remaining neural networks by simply imposing the residuals. So these 2 trainings were split in only data regression part for those neural networks in which we have data, and then a second training that involved only the residuals of the governing system of equations. And with this setting, we were able to consistently reduce the training times and also reduce the oscillations of our estimation during the training. As you can see, so the plots show more stable behavior during the training, and also the number of the values of the errors, the order of magnitude is decreased. But now we move to a more complex problem. So now this is a more realistic one in which the transmission rate actually is time dependent. So we have the same setting, same unknowns, and actually again the split training outperforms the joint one, both in term for sure in terms of training times, but also in terms of accuracy. But actually, when you are dealing with real data, they are strongly affected by noise. And if we wanted to use this data affected by larger noise, we were not able to handle this noise during the training. So what we did was to try to reduce the number of ODBs. And so we proposed a reduced SIR model that reduced from SIR unknowns to only I, along with the parameter, time-dependent parameter, that is the reproduction number RT. So in this case, with datum of infectious affected by larger noise, we were able to handle a little bit, but our result, especially for the estimation of the reproduction number, was not satisfactory. So what we did was to consider a datum that is usually less affected by noise in a real application, because the final goal, our final goal, was to use real data. And so what we did is to add a datum that corresponds to the hospitalizations, which is actually more reliable and, as I said, less affected by noise and error. But adding this new datum entails also the addition, for sure, of a new quantity of visitors, that is the number of hospitalization, along with a new parameter that is a time-dependent parameter here, sigma, which is the ratio of hospitalization with respect to the infectious, which is here is represented by an orange line. So actually, with respect to the previous result, even if we added 2 new unknowns, the results in our prediction improved. And especially with the split approach, we have higher accuracy and a shorter training time. So the last application is the one to real data. So we took the data from the Italian COVID-19 in the first 3 months of the pandemic in Italy. And we use the PIN model. So the model is really simple, because a simple SIR compartmental model, right? But even if the model is simple, we were able to catch the correct behavior and the correct estimation that was corresponding to the official estimation in Italy by Istituto Superiore della Sanità. And again, with the proposed split approach, we were able to reduce training time and to increase the accuracy. The last application that we did in epidemiology was short-term forecasting. So actually, we had this data set corresponding to the first 3 months. And we wanted to see if our model was able to give us some hint about what was happening in the future. So we split this data set in 4 temporal windows of increasing size. And what we did was to first train a pin in the first temporal window, use it in extrapolation for the future 2 weeks, and then retrain the same neural network and again use it in extrapolation for the following 2 weeks, and so on. So we took the first window, we train only on the magenta data, and then we use our neural network to extrapolate in the future. We did it again for the second window, and again the extrapolation, and so on for the third and the fourth window. And what we noticed was actually that at the beginning, it happens usually with epidemiological models, because you have few data, you are still not understanding what is going on in your what is going on during the disease spread. But actually, once the peak is reached, our pin method was able to perform a reliable short-term forecasting for the following 2 weeks. So to conclude, we have seen just application that we made in power mechanics, reservoir simulation, and in epidemiology. And in the first case, we were able with pins to reach a good matching between pin and analytical solution. We were able to reduce the training time and to reach convergence under inaccurate hypothesis with the sensor-driven framework that we proposed. We were able to reach a good parameter estimation with sensor data only in the most part of the homogeneous cases. And we were able to understand that the pin is able to learn the physics. So actually, the output of pin usually is always physically explainable. But the hard thing is to choose the proper constraints in order to make pins able to understand the physics that you want, let's say. And instead for the in epidemiology, we were able to estimate time-dependent parameter and reach a good time reduction with the proposed split approach. And even if the method is really simple, the results that we reached were consistent with the traditional and official estimations. And our final the goals future developments are to enlarge the application to real data. So actually, if we enlarge the period of the 3 months, we need to make the model more complex, because after the first 3 months, then we had the quarantine and other different dynamics that took place. And moreover, then after a short period, we also had the back sense. So we are working on that, on considering more complex problems in order to enlarge. Okay, this was my last slide, and I'm ready for questions.
Thank you, Caterina, for the very nice presentation. And I don't know if there's any question in the room. Please ask.
Didn't understand what you said when you were saying you reduced the C model to just one equation, certain quantity. What did you do there? Supposing that there are also a subset involved of X.
Again, we suppose the fact that the number of deaths were negligible with respect to the population, but actually we were also supposing that, let's say, we were only interested on the ratio of susceptible with respect to the total population, and not interested on the number of individuals belonging to the susceptible class, which was usually is not that meaningful for you. And so we're supposed to just be only interested in this ratio. So we were able to reduce another equation. Basically.
Any other questions? Also line, there's.
Maybe it's a stupid question, but I want to know why there's no static analysis of application quality.
Why? Sorry.
It's like it's a parametric study of number of collocation points or the location of this collocation points or the distribution of collocation points. I think this will affect the result.
Less affected.
So I think it will affect the result.
Yes, exactly. What I've shown at the beginning was exactly the distribution of the collocation points in time for the forward solution of pins, because a logarithm in time distribution gave us better results with respect to uniform one. So for sure, the results with pins are really affected by the distribution of and of the collocation points. But actually, what we cannot control is the number of is the distribution of training data points, because this is strictly related to the sensors that you have in the domain, or for example, in epidemiology, you have a datum per day usually, and so you cannot enrich this data set. But for sure, yes, there are a lot of factors, as said, for other parameters and other stuff that are affecting the results with pins. And so usually every time you start working with them and building a model, you need to perform a sensitivity analysis at the beginning that takes time, and then yes,
Yeah, and then now questions is about your maybe it's 22 page. Yeah, this one is like the input parameter is wrong. So I was wondering, your tools can still predict the result. Is because you set a low weight for the loss of PDs, and high weights for the loss of.
No, we didn't do it. So actually, the lost term weights are updated with the usual algorithm. So I don't remember exactly the algorithm that we did. Probably using the neural tangent kernel of the loss function. So they are probably updated during the training. So we didn't just decided to balance these two terms, and so focus more on the residual or on data. This is automatic, okay. But yes, what we simply did was to let the neural network understand which term was more reliable, I don't know how to say, okay, more important to minimize, and but actually something that for us it's extremely interesting, and we wanted to investigate it from a theoretical point of view, is how actually PIN is able to catch if, for example, if we train our PIN only with the datum, as the datum is only in a fixed location, the result is extremely wrong. Maybe it goes near the real solution around the datum that we give, but for sure, as we go farther from the datum, the prediction is completely wrong. But even if giving to the PIN, to the loss function, adding a residual, even if the residual has the same shape of the true residual, but as wrong parameters, this help the PIN to converge to the right solution. So it's even if we didn't balance anything, because actually when we usually want to model something, we think that our residual, our knowledge of the physics is good. We don't know if it's not. Maybe you have an historical study of measurements, geological formation and stuff like that. And so you think that your reservoir is governed by these parameters. So the materials are those. But then you have some data, and actually you realize that these data are not consistent with what is your physical knowledge of the problem. But actually, when we use data, we don't know. So we cannot just say a priori if the residuals are more reliable than data or not.
Okay.
And so we did it automatically during the training.
Thank you. Any other questions? Maybe I have just a small one, like for the final test case, like the pandemic one, when you spoke about doing prediction, was it a sort of autoregressive approach in which you're training the model in 2 weeks and then predicting for 2 weeks? Can you just maybe dig into that a little bit?
Yes. What is why we did so? Actually, yes, we train our pin for 2 weeks exactly, for the first 2 weeks, and then we use it in extrapolation for the following 2. Then we took the same pin as starting point, and we train in a larger temporal window. And you use it in extrapolation for the following 2. This is, for example, we compared it also with the non-physics informed neural network.
Okay.
And if you did so, actually the prediction in the following 2 weeks is completely wrong, or just it's just a guess. But actually, adding the residuals allowed us to more or less give to the neural network sort of continuity with respect to the solution. And so, but yes, we think that it's not